It's a great honor to be invited here to KAIST. It's my second time here in Korea, but first time I was only in Seoul, so it's really nice to see the rest of the country. Okay, so I'll be talking about a problem in combinatorics, the Erdős discrepancy problem that I worked on a few years ago and actually managed to solve. And the solution ended up being rather interesting, I thought. It is a problem in combinatorics. But to solve the problem, we needed to introduce ideas from number theory, from probability, even information theory. So it was, in many ways, I find the solution a bit more interesting than the problem, actually, to some ways. Oops. That was not what I wanted to do. Okay.
There you go.
Okay, so...
Yeah, so just these two.
Oh, these, okay, got it. Oops. Okay, so the Erdős discrepancy problem was one of the big open problems in discrepancy theory. So discrepancy theory is the study of how balanced you can make sequences of various types. So the simplest type of discrepancy theory concerns discrepancy of sign patterns. So for me, a sign pattern is just a sequence of signs plus or minus 1. Okay, so here's a sign pattern, plus 1, minus 1, minus 1, plus 1, plus 1. Okay, so a sign pattern, if you like, is just a function from the natural numbers, 1, 2, 3, 4, 5, to the signs, minus 1, plus 1. Okay, so of course there are lots and lots of sign patterns, and most of them look kind of random. If you write down a sign pattern of plus 1s and minus 1s, you expect about half as many plus 1s, sorry, half the time you should have plus 1s, half the time you should have minus 1s, and so your sequence should be very equally, evenly distributed in practice. So more precisely what that would mean is that if you form sums, like for example, if you sum the first n elements of this sign pattern, like for example you take the first 7 elements of a sequence and you sum them up, you get 3 plus 1s and 4 minus 1s, so you get a fairly small number, you get minus 1. And that's because this sequence is fairly well balanced. It has fairly low discrepancy on this interval of length 7. So that when you sum up all these, when you sum up these n signs together, you get something a lot less than n because there's a lot of cancellation. Okay, so we call the discrepancy of a sequence how much. Well, roughly, I mean, there's different types of discrepancy, but we, roughly speaking, the discrepancy of a sequence is sort of measures how much cancellation there is in the sequence. What you do is that you add up all the elements of sequence in some set, such as this initial segment of the sequence, and you see how large these sums are, and these sums we call the discrepancy. And one of the basic questions is how low discrepancy can you make a sequence? Like how balanced can you make a sequence? What's the smallest you can make sums like this? And this is the topic of discrepancy theory. It has some applications. If you want to do numerical integration, Monte Carlo integration, you often want to pick sequences that have very low discrepancy to minimize errors. But I won't be focusing on applications in this talk. It's a pure math talk. Okay, so all right. So there are many types of discrepancy and many discrepancy questions. Here's a simple one. So suppose you have some sequence. Let's say a finite sequence. Let's say n different signs: plus 1, minus 1, minus 1, plus 1. And you look at all the partial sums. You sum the sequence up to f1, f2, up to some fm. And you look at all the partial sums, and you want to make all the partial sums small at the same time. You look at all the partial sums, you look at the absolute value of the partial sums, and you take the biggest partial sum, and you want to make this quantity as small as possible. So you want to make all the sums small. And so how small can you do this? So this is actually an easy question to answer. So first of all, so one thing we know now in combinatorics, ever since Erdős introduced the probabilistic method in the 1950s, is that if you want to understand what's going on for, say, a sequence of signs or a graph or something, you should first understand what happens for random objects, like random sign patterns, random graphs, whatever. This often gives you a lot of insight. So one thing you can try is you just pick the signs randomly. You flip coins. If it's heads, you pick plus 1, tails minus 1, flip, 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 flip. You get a random sequence of coins, of signs, and then you can compute this sum. And it's actually not hard to compute. You can use something in probability called the Chernoff inequality, or the Hofting inequality. There's lots of inequalities you can use. And there are inequalities from probability theory which will tell you that if you flip n random coins and you get n random signs, normally this discrepancy, these partial sums will have size about square root of n. Okay, so the basic facts of probability is usually called square root cancellation, that when you sum n random things, you often get something of size square root of n. So that's what you do. That's what happens if you have a random sequence. The discrepancy is roughly root n times a constant. But in this particular problem, the random sequence is not the best sequence. There are much lower discrepancy sequences, and the simplest thing to do is actually just take an alternating sequence, +1, -1, +1, -1. So that's not random, and this has much better discrepancy. So if you take the partial sums of this sequence, like the first partial sum is just 1, and then 1 minus 1, that's 0, and then 1 again, and then 1 minus 1 plus 1 minus 1 is 0. So all the partial sums are just 1 and 0, and so the discrepancy here is just 1. And that's clearly the best you can do. There's no way you can make a sequence like this with discrepancy better than 1. So this is the best sequence you can do for this problem. And this is a very simple example of what's called a sub-random sequence, a sequence which behaves better than a random sequence. It's more balanced than a random sequence. So random sequences are often very good for getting reasonably low discrepancy, but sometimes sub-random sequences do even better. And sub-random sequences are very useful in numerical algorithms, but again, I'm not talking about applications in this talk. Okay, so that's a very simple problem. Now let's look at a slightly different problem. So again, we start with a sign pattern of n different signs, +1, -1, +1, -1. Now previously we summed partial sums. We only summed partial sums from f1 up to some fm. But now we ask for a much stronger notion of low discrepancy. So not only do we sum partial sums along initial segments of the sequence, but let's sum over every single arithmetic progression that we can find in the sequence. So if you take the sequence, you pick any arithmetic progression inside here. Say, for example, f of 3, f of 5, f of 7. You look at the sums on every single progression, and you ask, can I make every single progression small? So can I make f3 plus f5 plus f7 small, while also making f10 plus f20 plus f30 small, and so on. You make every single you try to make your sign pattern as balanced as you can on every single arithmetic progression at the same time. Okay. So again, if you try a random sequence, plus and minus ones are random for the coins, you'll find that this discrepancy is still about square root n in size. Okay, but is this the best you can do? Is square root of n the best you can do? So if you try the previous example, +1, -1, +1, -1, so that sequence was very good, very low discrepancy if you only take partial sums. But now if you allow arithmetic progressions, that's a very bad sequence. Because if you take, for example, the progression f of 2, f of 4, f of 6, f of 8, and so forth, all those numbers are -1, and you get a very big partial sum. So that sequence doesn't work. So, okay, and it's hard actually to make a sequence where all these sums are small. And there's a good reason for that. There's a theorem that stops you. Oops. Do that again. Sorry, it's the wrong button. Control L. Okay, now I remember that. Thank you. Okay, I won't need you next time I do that. All right. Okay, so there's a famous theorem in an area of combinatorics called, these slides are slightly out of date. Okay, so there's an area of mathematics called Ramsey theory. And one of the first theorems in Ramsey theory is something called van der Waals theorem from 1927. And what the theorem says is that if you take the natural numbers, 1, 2, 3, 4, 5, 6, 7, and you paint them different colors. So you pick some colors, say red, blue, and green, and you color some of the natural numbers red, some of the natural numbers green, and so forth. Then among these different color classes, one of these classes must contain a lot of arithmetic progressions. In fact, arithmetic progressions are of any length. So that's a basic theorem in combinatorics. And one of its consequences is that, so if you look at a sign pattern, a sequence of plus and minus ones, that's like coloring the natural numbers in two different colors, the +1 color and the -1 color. And so van der Waals theorem tells you that no matter how you color the natural numbers, either the +1 color or the -1 color will contain arithmetic progressions of any length. Which means that this discrepancy here, when you sum your sequence over arithmetic progressions, these sums must become unbounded. You must be able to make sums that are arbitrarily large. Okay, so the larger n gets, the larger this expression must get. And in fact, we know how exactly how much these sums are going to be. There's a fairly famous theorem of Roth. So Roth is famous for many things. He won the Fields Medal for several theorems, but one of them is this discrepancy theorem, in which he actually computed how big this discrepancy can be, and he said that actually it must be as large as about n to the 1/4 times the constant. So random sequences give you n to the 1/2, and you can do better than that, but you can't do any better than n to the 1/4. He used a technique which we now call the second moment method. And there's a much later, there's an example of Matuszek and Spencer that shows that in fact this is the best possible, that you can actually construct a sub-random sequence such that this supremum is a constant multiple of n to the 1/4. And so this is the right answer. Okay, so what do we found out? So if you measure discrepancy using only initial segments, you can get bounded discrepancy fairly easily. But if you measure discrepancy along all arithmetic progressions, you get unbounded discrepancy. So in the 50s, in the 30s, sorry, Paul Erdős asked, what happens if you consider an intermediate problem? Suppose you study sign patterns and you again measure discrepancy, but now you only consider what are called homogeneous arithmetic progressions. So progressions where the starting point, A, is the same as the step size. So like 10, 20, 30, 40 is a homogeneous arithmetic progression, but 11, 21, 31, 41, that's an arithmetic progression, but it's not a homogeneous arithmetic progression. So he asked what happens if you only look at homogeneous arithmetic progressions, what is the best discrepancy you can make here? So I think he was motivated by questions in number theory, because sums like this do show up in analytic number theory. So these sort of sums include the partial sums, but they don't include all the arithmetic progressions. So they're sort of halfway between the two problems that I already mentioned. Sorry. Okay. Right. So so this is a problem of So if you only have initial segments, you can make the discrepancy bounded. If you use all arithmetic progressions, the discrepancy must be unbounded. But if you only use homogeneous arithmetic progressions, what happens? Do you have boundedness or unboundedness of this discrepancy? And so Erdős thought, he posed the problem, he believed that this discrepancy must be unbounded. That as you make the sign pattern longer and longer, you must be able to make these sums bigger and bigger. You cannot keep all the sums here small simultaneously. Okay, so it's a simple problem, but actually it was really hard to make progress on the problem. So another way of phrasing the problem is that for any constant c, you must be able to make for any constant c, you must be able to make this these discrepancy larger than c as soon as your sequence is long enough. So there must exist some n such that for every sign pattern of length n, this discrepancy is bigger than c. That's another way of phrasing the discrepancy problem. Okay, so you can start studying the problem for very small values of c. So, for example, can you make this supremum bigger? Can you force this supremum to be bigger than 1? So that's very easy. The moment you have just one sign, plus or minus 1, you can just take that number f of 1, and that number must have size 1. And so your discrepancy must always be at least 1 the moment you have even just one term in your sequence. Okay. Now, what about 2? Okay, so suppose, what does it, how long do you need to make your sequence before the discrepancy has to be at least 2? So it takes a short while. Okay, so here's a sequence of 11 signs, plus 1, minus 1, minus 1, plus 1, and so forth. And one can check, it's a little bit tedious, but this sequence actually has discrepancy 1. So if you take any homogeneous progression, say for example 3 and 6, 3 and 6, see minus 1 and plus 1 add up to 0. So minus 1 alone, it gives you minus 1, minus 1 plus 1 gives you 0, minus 1 plus 1 and minus 1 give you minus 1 again. You never get plus 2 or minus 2. If you compute all the partial sums of the sequence on any homogeneous progression, you will find you only get 0, 1, and minus 1. So this is a sequence of length 11 where the discrepancy is only 1. And this turns out to be the longest that you can do. So the moment you have a 12th sequence of length 12, this discrepancy must be at least 2. So maybe I'll actually show this to you. It's a fun little argument. It's actually a lot like solving a Sudoku puzzle, if you actually. So yeah, is there a length 12 sequence, length 12 sign pattern, discrepancy 1, and the answer is no. So it's just, okay, so let me do a little table here. Okay, so what is a sign pattern? You have 12 numbers. Do I have enough space? Okay, barely. And you want to fill in these boxes, kind of like filling in the boxes of a Sudoku puzzle. And the rules are for every arithmetic progression, for example 2, 4, and 6, the sum of the numbers in this down here can only be -1, +1, or 0. They cannot be +2 or -2 or anything worse than that. So now you just try filling in the sequence. Okay, so 1, it can be +1 or -1. Actually, without loss of generality, I'll call it +1. If it's not +1, you just flip all the signs. So let's call it +1. Okay, now what about f of 2? Well, f of 1 plus f of 2 cannot be 2. Right? The discrepancy can only be 1, so this can't be +1, it must be -1. Okay? Now 3, we can't say anything about 3 right now because it could be either one is okay. But 4 we can do something with because f of 2 plus f of 4 can't be -2. So the 4 has to be +1. Okay, and then similarly 4 and 8 give you -1 over here. Okay, now we can say something about 3. See, f of 1, f of 2, f of 3, f of 4 cannot add up to 2. So this can't be +1, this must be -1. Okay, so this is -1, and then 3 and 6, that gives you +1 over here. Now, 1 through 6 can only add up to, it can't add up to +2, so 1, -1, -1, +1. This has to be -1, because otherwise this would add up to 2. Okay? 5 and 10, that gives you +1. Okay, 7, okay, so if you, okay, so 1, -1, -1, 1, -1, 1. This can't be -1, because this would add up to -2, so it has to be +1. Similarly, this one has to be -1, otherwise this sum would be too big. Now let's see, 6 is +1, which would make 12 -1. And now I think I should be done, but okay, let's see, I think 2, 1, 2. Wait, what have I done? Okay, actually made a. I haven't got a contradiction yet somehow. Okay, I have actually made a mistake somewhere. But 369, is that the problem? 369. Thank you. Yes. Yes. Okay. Thank you very much. Yes. Okay. So yeah. So this sequence is a progression where the discrepancy is -2. Okay, and so that gives you. That gives you a contradiction. Okay, so it is, it should remind you of sort of solving one of these Sudoku puzzles. Okay, so that was kind of fun. So you can try, what about 3? Okay, so what would it take to make a discrepancy length 3? So it was only in 2014 that we figured out the answer. Condiv and Situ in 2014, first of all, they discovered a sequence of length 1,160. So I'm not going to show it here, but there's a sequence of 1,160 signs for which the discrepancy is only 2. Which is very, very sub-random, actually. But more amazingly, they showed that was the best possible. That the moment you have 1161 signs somewhere in that sequence, you have to the discrepancy somewhere must be 2. Must be 3, actually. It cannot just be 2. So, in a sense, what they did was a giant version of this little Sudoku game, except that it's a lot harder. So, this is kind of like a 2-sat problem, if you know what that is. And this is like a 3-sat problem. So what happened here is that often once you knew some elements of your sign pattern, you could fix just one choice for another sign pattern, for another sign. But here now you often get 2 choices, and you have to do a lot of branching. So they actually made a massive computer calculation using a specialized FreeSat solver to show that, in fact, the discrepancy of any sequence of length 1161 must have length at least discrepancy at least 3. Okay. So actually, for a short time, this sequence, this proof they had had the world record of being the world's largest proof, because the certificate for the proof that showed that the FreeSat calculation was correct was 13 gigabytes long, which at the time was the largest proof ever made. Although they later simplified it to only 850 megabytes. And then later on, there was a completely different calculation, which was 200 terabytes. So, so they don't have the world record anymore. But but until they did this, it was not known whether you could have a sequence of discrepancy 2 or not. All right, so that's discrepancy 3. So discrepancy must be eventually at least 3. What about 4? So Conrad and Lisitta tried to compute what happens with 4. So they were able to construct a sequence of fairly long, 13,900 signs, where the discrepancy always stayed at most 3. All the partial sums were always between -3 and +3. But they did not know if this was the largest sequence. So now it's a 4-sat problem. It's really not at this size, it's really not beyond the not within the range of modern computers. And so it was not known actually whether this sequence had to discrepancy at least 4 eventually. Okay. So this is what I managed to do actually about 2 years ago. So I actually did solve the problem that the discrepancies are always unbounded. That if you take any sequence of natural numbers of sign patterns, eventually the homogeneous sums must be bigger in magnitude than any number you wish. So for instance 4. Okay, so one of the reasons why this problem is hard is that it's sort of, the answer is almost yes. I mean, the answer is almost no. That there are actually lots of sequences that are almost bounded discrepancy. Right. So okay. So not the random sequence. Okay. If you pick random signs ±1, you pick a sequence of length n. Random sequences have discrepancy about root n. This is another one of these Chernoff inequality or law of large numbers type calculations. But you can actually do a lot better than log n. Sorry, than root n. That there are sequences that have much better discrepancy than root n. So, for example, this length 12 sequence already is fairly sub-random with only discrepancy, 11 sequence, discrepancy 1, or this length 1160 sequence, discrepancy 2. So what are some non-random sequences of low discrepancy? So here's one example which actually, it isn't sub-random, at least we don't believe it to be sub-random. It's about the same size as the random function, but this will be an important function later. So one example to consider comes from number theory. So there's a very important number theory function which is a sign pattern, which is what's called the Liouville function, lambda. It's a function defined to be +1 when n is the product of an even number of primes, and -1 when you're the product of an odd number of primes. So 4 is 2 times 2, that's 2 primes. So lambda 4 is +1. 30 is the product of 3 primes, 2, 3, and 5. So lambda 30 is -1. Okay, so it's a sign pattern, +1, -1, -1, +1. So it has a special property. It is what's called completely multiplicative. So the special property of this function is that when you take lambda of any product, okay, so that's sort of easy to see from the definition. And so one consequence of that is that if you try to sum this function on any progression, you can pull out lambda of a. So this is lambda of a plus lambda of 2a up to lambda of ka. This is you can just pull out a factor of lambda of a from the sum, and this expression is just plus or minus just the first partial sum of lambda. So, yeah. So because this formula lambda of a plus lambda of 2a plus up to lambda of ka. It's just factors lambda of a plus lambda of 1. Okay, so if you want to understand the discrepancy of this sequence on homogeneous arithmetic progressions, you just need to understand partial sums. So the basic question is how fast do the partial sums of the Liouville function grow? Okay, how fast does this grow in K? So this turns out to actually be a major open problem. So of course, the first K sums they grow by they can't grow faster than K, certainly, and we do know that they grow a little bit slower than K because of a basic theorem in number theory called the prime number theorem. It's believed that this sequence behaves randomly, so that these partial sums should grow like square root of K, just like they do for a random sequence, give or take a log or something. But that's really hard. That turns out to be equivalent to the Riemann hypothesis. Okay, the fact that the partial sums, so we believe the partial sums go like root K, but we don't know that, or we conjecture that. That's the Riemann hypothesis. But what we do know, that we can show that they must grow at least as fast as root K. So it is known that there are infinitely many K for which this sum is actually bigger than the square root of K. For those number theorists in the audience, that's because the Riemann zeta function has at least one non-trivial zero on the real line, on the critical line. We think all of them are on the critical line, but we don't know that. But we know at least one of them is, and that's enough to just give you the lower bound. Okay, so this Liouville function is not a low discrepancy sequence, but only because there's a zero of the zeta function on the critical line. So that's kind of weird because this question is a combinatorial question, and this number theoretic fact somehow shows up, at least for this function. Okay, so that is not a counterexample to the discrepancy problem, thanks to this zero of the zeta function. But there's another example which is better, which are the, what are called Dirichlet characters, which are also important in number theory. So a Dirichlet character, say chi, is a sign pattern, or more generally, you can take complex numbers as well, but let's say plus minus 1, which is completely multiplicative, just like the Liouville function, but it's also periodic. So it also repeats itself. But it doesn't necessarily take values minus 1 plus 1. It is allowed to vanish. And in particular, it's supposed to vanish if for numbers that are co-prime to numbers which are not co-prime. That's a typo to this period. Okay, so a good example of a Dirichlet character is this guy called chi3. This is the sequence which is plus 1 when n is 1 mod 3, minus 1 when n is 2 mod 3, and 0 when you're 0 mod 3. So this character looks like this. Oops. Plus 1, minus 1, 0, plus 1, minus 1, 0, plus 1, minus 1, 0, and so forth. Okay, so this is a Dirichlet character. And these guys have very low discrepancy. So like if you take any partial sum of this sequence, you always get plus 1 or 0 or plus 1 or 0. You only ever get plus 1 and 0. And you're completely multiplicative, so once you know the partial sums, also on any homogeneous arithmetic progression, these characters also have bounded discrepancy. So so every single partial sum here is either 0 or 1. So this is a very low discrepancy sequence. But it doesn't give you a counterexample to the discrepancy problem because there's zeros here. Okay, so the Erdős discrepancy problem only considers sequences where you only allow plus 1 and minus 1. But this sequence is 0 1/3 of the time. Okay, so it's sort of 2/3 of a counterexample to the discrepancy problem. 2/3 of the time is plus or minus 1, and the discrepancy is non-zero. It's 2/3 because this is a character of period 3. If you picked a character of period 11, it would be like 11th of a counterexample, and so forth. So using Dirichlet characters, you can make sequences, which I say, sort of 99% counterexamples to your problem. That they are plus minus 1s most of the time, but the discrepancy is bounded. And this is really your first hint that this problem is going to be quite difficult because you're going to have to somehow deal with these almost counterexamples at some point in your argument. you can modify this example a little bit. You can try to replace the zeros by plus or minus ones. So this was considered in 2010 by Borwein, Choi, and Koons. So they considered a sign pattern which is like chi3, except so it instead of looking at the last digit, the last digit of your base 3 expansion, which is what chi3 does, it looks at the last non-zero digit of the base 3 expansion. So you define it to be plus 1 if you are 1 mod 3 times the power of 3, and minus 1 if you are 2 mod 3 times the power of 3. So it's the same sequence as the Dirichlet character. But you replace the 0, so this is 3 times 1, so it's plus 1. It's 3 times 2, so it's minus 1. This is 3 squared times 1, so it's plus 1. This is 3 times 4, and 4 is 1 mod 3, so it's also plus 1, and so forth. So this is a sequence now with no zeros. You've replaced the zeros by signs, and the partial sums are now pretty small. So there's actually a very cute calculation. If you compute the partial sum, if you sum the first k terms in this sequence, that's always equal to the number of ones in the base 3 expansion of k. So for example, if you sum these three numbers, 1, minus 1, 1, you get 1. And 3 is 1, 0 in base 3. It has 1, 1. And so this you get a 1 here. 4 is 1, 1 in base 3. So and the partial sum is 2, and so forth. So there's a very cute formula for the partial sums. So the sum is equal to how many ones you have in the base 3 expansion. Okay, and that's unbounded. Okay, as you make k bigger, you can have more and more ones in your base 3 expansion, but it grows very slowly. The number of ones you can have is only like log k, log base 3 of k. That's the most you can have. So that's very sub-random. Remember, random sequences, these things can go like root k, square root of k. This is only log k. So you can find sequences that are almost bounded discrepancy. They only grow logarithmically fast. And these examples, all the examples we know that are bad, they all come from Dirichlet characters. Dirichlet characters are the enemy in this problem. So somehow you need to somehow isolate these characters and somehow get rid of them. Okay, so it really suggests that number theory has to be involved to solve this problem, because these are very number theoretic objects. Okay, so people have worked on this problem for many decades. So the first big breakthrough really was about 7 years ago, in 2010. So Timothy Gowers, a good friend of mine, he organized one of these things called Polymath projects, a Polymath project. So a Polymath project is when you get many mathematicians all over the world to collaborate on solving a single problem over the internet. So you use maybe a blog or maybe a wiki, something like Wikipedia, and you get all these people talking, trying all these different things, and so not even throwing out things that they don't think are going to work, because even though they can't see how to finish the problem, maybe somebody else will be able to fix it and so forth. So there were, he had at some point about a dozen or so people, including myself actually, working on this problem for several years. It ran for about 2 or 3 years, and it didn't actually solve the problem completely. For example, they found a sequence of length like 1,000 with discrepancy 2, shortly before Konev and Lisitsa. And they had a number of very nice observations. But one of the things that they've discovered, roughly speaking, so this is simplifying things a little bit, but they managed to show that to show somehow the role of number theory, that for this problem, the most important sequences in this problem were the completely multiplicative sequences, like the Dirichlet characters and the Liouville function. That if you wanted to solve the discrepancy problem, roughly speaking, it suffices to check to solve it only for sequences that are completely multiplicative. If you can solve it in that case, then you can solve it in general. You actually have to prove something a little bit stronger for these functions, but let me not discuss the technical detail. Okay, so this leads to a simplified version of the problem. So rather than take an arbitrary sequence, just take a multiplicative sequence. and ask for any multiplicative sequence of plus and minus 1s, are the partial sums of a multiplicative sequence always unbounded? So that's an easier version of the problem. Now, how you do this reduction, I'm not sure how much time I have. Maybe I will skip the description of the proof. Let me just say that it uses tools from Fourier analysis. Multiplicative functions you can think of as like characters on the natural numbers in some sense. And Fourier analysis lets you decompose arbitrary sequences into characters. And so you basically break up an arbitrary sequence into linear combinations of these multiplicative functions. And you do some averaging, but I think I will skip the actual reduction. Okay. So, so the model problem now is that you take a multiplicative function, such as the Liouville function, and the basic question is, can you show, for example, that the sums of the partial sums of the Liouville function are unbounded? So that is a basic model problem. Now, in this particular case, as we saw before, the answer is we can, because the Liouville function turns out to be connected to the Riemann zeta function, and you can use zeros of the Riemann zeta function to answer this question. But that's a very special property of this one particular function, Liouville function. Most multiplicative functions have nothing to do with the zeta function. And so you would like a way to answer this question that doesn't use facts about the zeros of the zeta function. So this is a model problem. Okay. So you can take a probabilistic viewpoint. So we believe that the Liouville function behaves like a random sequence. That's one of the basic beliefs in number theory, analytic number theory. Now, as I said before, if you take a purely random sequence of plus and minus 1s, the partial sums, the first k sums, should go like square root of k. Right? This is a very standard computation in probability. And if you use tools from probability, in particular something called the second moment method, you compute means and variances of these sums. What you can find is that even if your function is non-random, if you have a sign pattern which is not random, you can still show that these sums grow, maybe not as fast as root k, but you can show that they are unbounded at least, as long as you can control covariances, as long as you can control these sort of correlations. So you sum things like f of n times a shift of f of n. So these are called correlations or covariances. If you can make these small, if all these covariances are small, then you can use tools from probability to show that this sum must be big. Basically, you can show that sort of that there's somehow the variance of certain randomly chosen subsums of the sum are big. So actually, the real problem is to understand these covariances. So then you are interested in studying sums like this. You take Liouville function of n and then Liouville function of, say, n plus 3 or n plus 2. And you want to understand these sort of correlations. Now, this unfortunately is a very hard problem. So there's a conjecture of Chawla in number theory that says that these sort of correlations should be small. That if you sum these sort of sums up to x, there should be little o of x. That means that when you divide by x, this goes to 0, as x goes to infinity. So this particular claim is a conjecture of Chawla. If this was true, this would imply, at least for Liouville function, that the these sums are unbounded. Unfortunately, this conjecture is open. It looks about as hard as the twin prime conjecture. So this conjecture is about asking whether n and n plus h both have the same parity of prime factors, like both have even number of prime factors, both have odd number of prime factors. That should happen about 50% of the time. That's sort of what the Chawla conjecture says. And that's very close to the twin prime conjecture, which is asking whether two numbers like n and n plus h, how often they're both simultaneously prime. And that's open. So we can't prove that conjecture yet. But what I managed to do about 2 years ago was that I managed to prove a weaker version of this conjecture. So if you don't sum this conjecture, you don't sum these numbers directly from 1 to x, but you insert this weight. You sum this quantity lambda n plus h, but you divide by n. then the trivial bound for this sum is the sum of 1 over n, the harmonic series, which is of size log x. And I was able to show that there was a little bit of cancellation in this sum, and so this sum is a little bit smaller than log x. So there was some cancellation when you sum in this way. And that turns out to still be good enough. Okay? If you can prove this, then you can show that the partial sums of the Liouville function are unbounded. And I could do this for every completely multiplicative function had a bound like this, except the Dirichlet characters. Dirichlet characters do not do this. Like if you look at say chi3 of n, chi3 of n plus 1, then maybe some like this. Okay, this sum is actually bound. This sum is actually grows like log x. Basically, because whenever this is plus 1, this will always be minus 1. Right? There is some correlation between these two quantities because of the periodicity. But this is a non-periodic function, and this doesn't have that periodicity. So somehow the Dirichlet characters were the only characters for which you didn't have this property. But you can deal with the Dirichlet characters separately by a separate argument. So somehow they're the worst enemy, but everything other than the Dirichlet characters are okay. But they're the only characters that really cause the most problems. Okay, so Liouville function, for example, does not cause any problems. Okay, so I was able to prove this number theoretic estimate, which was the key ingredient in solving the Erdős problem. Okay, yeah. So why this funny sum? So it's more natural to sum numbers from 1 to x without any weights. So why do you put this 1 over n weight? So roughly speaking, this 1 over n weight is like multiplicative Haar measure. Right? So when you integrate, often when you do analysis and you want instead of integrating a function, say from 0 to x, it's often very natural to instead integrate a function using dt over t rather than dx. This is multiplicative Haar measure rather than additive Haar measure, because this type of integral has good properties with respect to multiplication, and of course the standard Haar measure has good properties with respect to translation, but this has good properties with respect to dilation. And these sort of questions are actually they're more multiplicative than they are additive. So it's actually better to use something that looks like a multiplicative Haar measure. That's sort of roughly where this 1 over n comes from. Okay, so now it's going to get a bit technical, I'm afraid, as part of this talk, just to explain how to prove this theorem here. Yeah, so once you decide to divide by this 1 over n, you get this funny. So it's discrete. So for integrals, you have this very nice change of variables. Okay, so if you integrate, let's say, from 0 to x f of t to t over t, you can always change variables. You can dilate by any factor q, and okay, you can always change this integral you can scale it by q, and you get this integral. You just make a change of variables t prime equals qt. Okay, so when you use multiplicative Haar measure, you have this nice dilation invariance. Now, it doesn't quite work for summation, because when you take the natural numbers from 1 to x and you multiply by q, you don't get all the natural numbers from 1 to x, you only get the multiples of q from 1 to x. So you get a slightly worse formula. So when you sum the numbers from f of n over n from n to x, you can dilate, you get f of n over q over n, but you also have to multiply by this weird factor here. You only restrict to multiples of q, and then there's a normalization effect of q that shows up. But apart from this unpleasant factor here, this sort of arithmetic factor here, you have a dilation invariance, which is sort of the analog of this continuous invariance here. So you have this dilation invariance, which combines very well with the multiplicative properties of the Liouville function. So the Liouville function has this particular property because it's multiplicative. Lambda of, if you multiply n by any prime p, lambda pn is always minus lambda of n, because lambda of n, remember, is minus 1 for the number of prime factors of n. So if you multiply by p, you add one more prime factor. So you can use this, you can combine these two expressions together, and you can use them to make this sum better. So the funny thing about analysis, so this is an analysis problem, is that when you want to make a sum better, usually what you have to do is you have to make it uglier. You have to make this is only one summation, but if you can transform the sum to have multiple sums in here rather than just one sum, then you have more averaging and you can do more things. So you can start using this sort of invariance to make this sum uglier as far as but more tractable analytically. So what you can start doing is that you can dilate. Okay, so lambda of n is negative lambda of np, and lambda of n plus. Let's say we're studying this sum, lambda of n plus 1 over n. So you can dilate this by p, dilate this by p, okay, and you get this, and then you can do a change of variables. Okay, you change n to p times n, and what you find is that you can transform this sum, this correlation involving 1, a shift by 1, to a correlation involving a shift by some other shift p for some prime p, times this weird factor where you have to restrict to multiples of p. But let's ignore this factor for the time being. So this correlation involving shifts by 1 can be related to correlation involving shifts by p for any prime p. And then you can average over all those shifts at once. And what you can find is that you can control the single average to now a double average, where you not only do you average n from 1 to x, but you also average over some prime p. You average over primes p in some set, and you can pick what set you want. And it's actually important that you get to pick what set you want. So you can change this sum into this sum, which looks a lot worse. Okay, it's a lot more complicated, but there's more averaging going on here, and there's more chances that you can make something work when you have in analysis when you have more averaging going on. Okay, so now we have to understand this double sum. Now, as I said, the problem is that there's this weird weight here, which depends on what n is doing mod p, and that weight is unpleasant. But on average, this weight is 1. Okay? If you pick a random number n, then it will be divisible by p 1 over p of the time. And so this weight here is, you can think of sort of a random weight which on average is of size 1. Now, if we could replace this by 1, this would be a much simpler average. So if instead of this average, we just had this average here. This turns out to be something that we can understand. This double sum can be attacked by methods of analytic number theory, including something called the circle method. To make a long story short, there was a big breakthrough last year by Matamaki and Matsuo, two number theorists, who were able to show that these sums were all small, basically. So using a lot of high-tech tools from number theory, they could show that sums like this, these double sums, were actually quite small. Small enough that for what we need for this application. Okay, so this sum was fine, but the only problem was that we had this extra weird factor here, which involved the residue class of n mod various primes. Okay, so the hard part is to understand what the role of this extra weight is. If you pick n randomly, so the Chinese remainder theorem tells you that so if you pick a number n at random, then n mod p will be distributed at random uniformly between the residue classes mod p, and you pick another prime cube, the residue classes n mod q will also be distributed uniformly, and the Chinese remainder theorem tells you that these sort of residue classes behave independently of each other. So these guys behave like independent random variables. And now, unfortunately, as n varies, these guys vary as well. These signs vary as well. But if they didn't vary, if these were somehow fixed coefficients, and you only vary, and the only variation came from these signs, then what you'd be doing is that you'd be summing independent random variables. And this is something that probabilists understand very well. And so if you can use tools from probability so that say that if these signs were somehow fixed, that they didn't depend on n, they were just some fixed signs, then this expression would actually usually be very small. Okay? And there's a specific tool called Hopkins inequality, which you can use to say that this expression is almost always very small, that there's only an exponentially small probability. There's only an exponentially small set of residue classes which will cause, in which the sum would not be very small, this double sum here. Now, of course, these sign patterns do depend on n, and that's very annoying. But if you use this Hopkins inequality, what you can show is that this type of sum will usually be small unless there is some weird correlation between this factor here and this factor. If these factors somehow conspire to not cancel each other out, sorry, to cancel each other out. So if there's some sort of conspiracy that between so what you can do is for any n, you look at all this, you look at all the values of the Lua function near n. So you look at the sign pattern near n. So you take like h different signs for some h, like square root x or something, and you look at the residue classes n mod p, and these are two different functions of n, and these two functions have to be highly correlated in order for this sum to be large. If these sort of two statistics behaved independently, you can use Hopkins inequality to show that this expression has cancellation. So the only problem is if there's a lot of correlation. And it turns out that the correct way to measure correlation comes from information theory, which was a surprise. So there's a concept in information theory called mutual information. So you can pick n randomly, and then you have these two random variables. On the one hand, you have the sign pattern, and on the other hand, you have these residue classes. And if there's a lot of mutual information, in the sense of Shannon entropy, between these two random variables, then this sum can be large. But if they have low mutual information, you can show the sum is small. So the only problem, the only enemy remaining, is if these sign patterns share a lot of information, that they're somehow very biased depending on what the residue classes of n mod p are. Now, we can't stop that from happening, unfortunately. It is possible that these signs are somehow very sensitive to n mod p. Like maybe when n is 1 mod 11, these signs are biased to be plus 1 minus 1 plus 1, to be one particular sign pattern. But when n is a different residue class, maybe they're biased to be a different sign pattern. There could actually be a lot of shared information. But the last trick is that these primes p are drawn from some set of primes, which I call script p, and you get to pick which set of primes to use in your argument. And it turns out that each set of primes sort of behaves independently, and and it is possible that this sign pattern could share information with one set of primes, but that uses up some of its entropy. And then there may not be enough entropy left to also share information with a different set of primes. And you can formalize all this using what I call the Shannon entropy inequalities. That each set of primes has its own different sort of carries its own sort of separate amount of information, and there's not enough entropy in the sign pattern to correlate with, to share information of all of these different residue classes at once. And so by using actually the pigeonhole principle, it's the final thing, you can find a set of primes for which there is not much information shared between the sign pattern and these residue classes. And then so by using finally the pigeonhole principle, you can get low enough correlation that the tools from probability, Hopkins inequality, can start helping you to get cancellation, and then that is finally what lets you solve this problem. So it's a really, it really surprised me when I was working on this that more and more tools from different areas of mathematics kept showing up to solve the problem. But yeah, so finally we actually are able to finish off this conjecture. So I think that's the end of my talk. So thanks very much.